Good afternoon, everyone. Today, I'm Zhang from Tianyu University of Hong Kong. Today, I will introduce our research work for the time series database. In this work we introduce a novel cloud-based storage model with a new metadata management for this time series data. So this is the outline of this presentation. So let's first go to the background to show what is the performance monitoring time series system. Usually for this kind of system, we try to collect some performance metrics, such as the CPU utilization or some memory usage information. And popularly utilized system may be the Prometheus, or we have the Timescales DB or InfastDB for this kind of the data. And now we have the trend that we move more of the service and the data to the cloud. And also for this, we have the trend to move the data to the cloud object storage. So as shown in this architecture, with the typical architecture, now we try to move both the query ingestors to the cloud-based server, and we move the data to the cloud object storage, such as the Amazon S3 or the Google's cloud object storage. In this way, we have some advantages that we have a high scalability, and the cost can be controlled with the data size. But the disadvantages is also clear that we have now a prolonged access latency compared with the local SD and HDD. We may have several times and up to 1,000 times higher latency. And now let's see what is really the time series data and how we define it. So usually it is defined by a set of tags, and showing in this example to define the information, CPU information for one core in one server. We utilize this combination of the tag pairs to define the distinct time series. So here we have three tag pairs. The first one is the time series metric and also the node information, CPU information. And then when we do the query, still we need this part of this tag pairs combination to indicate the filter range. So as shown in this query example, we try to find the CPU usage information in the node 1. Yeah. So here the tag pairs, which is the metadata for the time series data, is very important. And then let's see how we organize the time series data in existing system. So first, we have the tag-based indexing based on our aforementioned information. And with the time going on, we need to collect the data more and more. So as shown in this example, we have a time-partitioned data blocks. So inside each time partition, we may maintain the metadata and the corresponding time series data in this one data block. In this way, we can directly access the data in each time partition. Then, with this organization and move the data to the cloud-based object storage, we found that there are significant performance degradation. And showing in this figure that we compare the performance with the cloud storage and the local storage, you may find that we may have several times higher latency. So this is because the fundamental characteristics of the cloud object storage, as we mentioned. And besides this, we also have other issues. So first and second issue here is that we have severe read amplification, because you may find that the queries need to retrieve significantly more data than we actually require. And also, the metadata may be repeatedly stored, maintained in each time partition. And this high latency from the cloud storage may make these two issues severe. So in this paper, we try to solve these two issues. So for the read amplification, we show the factor. So in this example, we access the 10 time series in 1 hour. So with different baseline, for example, the cloud-based Cortex, or we have the packet or the JSON time series format. Actually, we mainly need to access all the metadata for this time series. So we have a higher reamplification due to the unnecessary data fetched and the I/O volume. On the other hand, we analyze the time series data set we collected with 500,000 time series and across 200 time partitions. We found that over 70% of the tags, they are repeated across multiple time series, and also some tags may be shared in more than 90% of the time series. So this gives us the opportunity to reduce the metadata size and optimize the management of the metadata to improve the query efficiency. So with this, we propose CloudTS, which is a lightweight time series storage model, and it can be seamless integrate with the existing time series database. The basic idea here is that we separate the management of the metadata and the data. In this way, this brings the opportunities to optimize the metadata management and data access separately, so to try to solve the metadata redundancy and the reamplification. So for the metadata part, we have some new architecture, for example, the tag dictionary and time series tag mapping. And also for the data part, we try to propose a new TS object organization for the time series data. So first, for the tag dict, we build a global tag dictionary, which is a Patricia tree-like structure. With this structure, we can have a global encoding for every unique tag pair, and in this way, after this, we can utilize this encoding number to represent this each unique tag pair in different time partitions. And also, we have a time partition where tag arrays to manage the metadata information in each time partition. And shown here, for the CPU core 1, the global encoding here is 1. And in the time partition 1, the tag arrays index 0 is utilized to represent this time partition CPU core tag pair. And similar in the time partition 2, the index 4 is utilized to represent this tag pair. So this significantly reduces the reference size for the tag pairs. And with this encoding, we can build up a very straightforward time series and tag index. So for one time partition, we build up one TT mapping. So still utilize the example for the CPU core 1. So now the tag 0 is the corresponding tag pair. So we can have the bidirectional indexing. First, for example, if we try to search the data time series 2, we can directly find in this row, and you may find that corresponding tags 3, 4, and 6, 7 are involved. And for example, and also for the tag information, if we try to find the involved time series, we can still utilize the column data. So we find that time series 0 and 1 contain the tag 0. And you may find that for this kind of matrix, it is a sparse matrix, so we can further compress it. And because here we only have the 0 and 1, so 1 bit can be okay. So we try to have a variant of the compressed sparse row, and we remove the value array. Here we build up our time series metadata mapping compression. After the compress, we only have 2 arrays, one for index in each time series and one for the pointer for each time series. Then it can significantly reduce the space utilization, space overhead. And also we show how we organize the data in the object. As we mentioned before, for each query, we need to indicate the combination for the tag pairs. So each query here also needs to access a small subset of the correlated time series over the aligned time ranges. And also we found that there are trade-offs between the object management and the access speed, because you may imagine that with each object with fewer time series, we may need more time series object lookup, and in the other hand, with more time series in each object, they may also introduce high redundancy. So we propose a group-based TS object. The key idea here is to group the related time series into one time series object based on the tag similarity and the tag selectivity. So this information can get from the TT mapping. So for the details, you may check it in our paper. In this way, we try to maximize the query locality to reduce the reamplification. And then we introduce our evaluation results. So we integrate our CloudTS into the Cortex, and the evaluation is based on the Amazon Cloud environment, and we compare with the original Cortex method and some Parquet and JSON time series system, JSON time series format. So for the production environment evaluation, we can improve the end-to-end query latency by 1.43 times, and we also show the data transference throughput. So you may find that we may have a stable query throughput, and here we have periodically uploads throughput. So this means that for each time partition, we may upload them when we process the corresponding time partition. Also, we show the scalability. So in a long-term retention condition, which may spanning around 200 partitions with total over 1 million unique time series, the corresponding tag dictionary size is consistent. And also, inside each single partition, we have consistent usage for the TT mapping and tag array. And similar for a high-frequent label churn, which means that in each time partition, we have significantly different number for the time series. So in each partition, we may have up to 3 million short-lived time series. Or for the smallest one, we only have several thousand time series. So this, for this result, you may find that we have significantly latency overhead, because now we need to go through more time series metadata. But for the memory usage, you may find still we have the consistent tag dictionary usage, and similar, we have an acceptable memory usage for the TT mapping and tag array for each single partition. Yeah. Then let's go to the conclusion part. So in the CloudTS, we propose a time series storage model designed for cloud object storage. And the key idea here is to separate management for the metadata and data to reduce the reamplification. And we have the novel metadata management to reduce the metadata redundancy. And the benefits, so we can introduce up to, we can have up to 36% lower query latency and 30% less data access. Yeah, and that's all for this presentation. Thank you. Yeah.